Good morning and welcome to this next lecture on sound and structural vibration. So we ended up in the last class over here where we found pressure due to an input volume velocity and due to a force applied to the structure. Similarly, we found the velocity at the common point when a force is applied and a volume velocity is given into the cavity. Okay. So we will just make some physical comments. Okay. So if I put this together in a matrix form, I get P and U given by ZA into SYS plus 1 plus ZAYCS. Okay. Then ZA by 1 plus ZAYCS F here and Q here. Okay. Then U is given by YS by 1 plus ZCA YS, and this is with a minus sign. Okay. YS SZA by 1 plus YSZCA. Okay. I have to make the comments here only, or I take a new page and write again. Okay. So let me make the comments here. So if there is no flow into the system, that means my Q is a 0. Okay. Then if a force is applied, okay, a pressure and a velocity are generated. Okay. And if the system is in vacuum, okay, suppose then ZA is actually 0. Okay. Then pressure is actually 0. You can see the pressure is 0 if the system is in vacuum. Okay. Then the particle velocity is just F over ZS. Okay. So this term goes to 0. Particle velocity is just F over ZS. Okay. Now if the system is not in vacuum, okay, a pressure gets generated, okay, which opposes the applied force and thus reduces the particle velocity to U, which is given by this entity with a denominator. Okay. And if in addition to that a flow Q is given, a pressure increment of QZA should have happened. Pressure increment of QZA should have happened provided ZS was infinity or YCS was 0. But as ZS is finite, okay, the pressure is reduced since the structure deforms, and therefore you have this additional denominator. You do not get that much pressure. Okay. Similarly, if F happens to be 0, okay, then Q is the inflow. When ZS is infinite, YCS is 0. Okay. Thus the velocity is going to be 0. The velocity at the interface is going to be 0, but a pressure is going to be generated. A pressure is going to be generated. Okay. So related to the pressure there is no velocity since the structure is infinitely rigid. Okay. If the structure has a finite impedance Zs, okay, firstly the pressure generated is lowered Q into Za divided by this, because the structure now takes up some deformation, okay, and the corresponding velocity is applied by multiplying with S over Zs. It is a negative. Okay. So, this matrix makes physical sense. Okay. Now, let us look at the actual system, which is this. So, there is a structure. So, we will call this, what do we call this topic? We will call this vibrating plate interacting with a cavity. Okay, vibrating plate backed by a cavity interacting with a cavity. So, the diagram I will use is very similar to what is shown in Kimbrannen's paper. So, this is a vibrating structure and it is backed by some arbitrarily shaped cavity. Okay, that cavity wall is rigid, this wall is rigid. Then there is this volume V inside. Okay. There are forces applied to this structure that is described by Y. The structural surface is described by Y bar, a vector Y bar. Okay. And it has a surface given by SF. It has a surface given by SF. And then within there are acoustical sources. That source distribution is described by S x comma omega. So, the 3D geometry of the cavity is described by the vector S x bar, and the plate surface, which is a plane, is described by Y bar. Okay. So, now what do? We describe now the acoustic pressure. We describe the acoustic pressure using the modal sum. Pressure is described by, okay, where we assume that the mode shapes are the rigid walled mode shapes. That means the panel was rigid. Okay. So, that is equal to summation of n equal to 1 to capital N psi n of x a n of omega. These psi n's are uncoupled acoustic mode shapes. Okay. And we take n of them. So, that is why the index n goes from 1 to n. So, we take n acoustic mode shapes. Okay. And then a n of omega are the amplitudes. Okay. or also called modal participation factors, modal participation factors. Okay, and we can write this in a matrix in a vector notation. So we will do it psi transpose A. The bar indicates vector. Okay. Similarly, the plate velocity described by y is again a sum, this time over small m till capital M of phi m of y into Bm of omega. Okay. Here what are phi m's? They are the uncoupled plate modes. Okay, that means plate vibrating in vacuum, not backed by a cavity. Okay, then Bm's are the amplitudes or modal participation factors. Okay, and in a matrix notation or a vector notation, this F bar transpose B bar. Okay. Now these uncoupled modes, they satisfy orthogonality. That's the advantage. So let's write orthogonality. What is that orthogonality? We say V is equal to integral over the volume, okay, psi n square of x dV. Okay, psi n into psi n integrated gives me this value V. Similarly, Sf is equal to integral over the panel area, plate area, phi m square of y. So phi m of y into phi m of y integrated of panel gives a value. That means if this index is different, phi m into phi r integrated will be 0. That is the orthogonality. Okay. So now let us look at the acoustic space. Acoustic space. Okay. So the equation is del square P plus k square P is equal to, there will be a component coming from acoustic sources, okay, sources. There will be a component coming from plate deformation, and therefore a volume velocity from there. Volume velocity from there. Okay, so let us look at the units now. The units of this are pressure over length squared. Okay, pressure divided by length squared. Okay, so let us take the force first, mass into acceleration divided by L square. Now I have pressure units, divide by one more L square, this one. So I have m over t square length cube. Okay. So this is density. So I will have acoustical density over here. Okay, that means these terms should have the same units. I am trying to generate those terms. So density is there, okay, and then I need something over T square, and the acoustic source has to be a volume velocity. Acoustic source is what? A volume velocity source. Okay, volume velocity with some spatial distribution. Okay, so this is going to be, the remaining is what I just 1 over T square. So how do I do that? I will say it is volume velocity that gives me 1 over volume over T per unit volume. Volume velocity per unit volume. This will give me 1 over T because volume cancels out, and then I will put j omega to make it 1 over T square. Okay, so I have j omega and an S which is volume velocity per unit volume. Okay, so this is, so S has volume velocity per unit volume. Okay, so that's how I get. Okay, now what about the plate? What about the plate? The plate has its own velocity u, plate velocity locally. Okay, locally there is a plate velocity. Okay, so that has length over time units. Okay, so now what I do is that the plate is a plane, in 3D space. Okay, so out of the X space which is 3D, okay, it occupies, so one dimension is reduced, one dimension gets reduced. That means we remain in a plane, so one dimension is dropped. Okay, and that becomes my y. So I put, so what do? I do take the velocity, okay, and then I multiply by a certain delta function which has dimension in it, whatever dimension. Okay, let me put z here temporarily. Okay, so what this gives me is length over time divided by length. So I have 1 over time now. Okay, I have 1 over time. So what do? I multiply by j omega, that gives me 1 over time square. Okay, and I multiply by a density, okay, the fluid density, which gives me mass over L cube. Suppose you follow. So then what do? I have rho 0 j omega velocity locally, okay, multiply by a certain delta. That delta takes me from x space to y space, the x dimension 3D to y dimension 2D. That is what that delta z does. Okay. So now, given this situation, I am going to substitute for my pressure the modal sum. Okay. So what does that do? I get del square the modal sum over n, okay, then psi n x comma omega sorry psi n x a n of omega, okay, plus k square summation over n psi n of x a n of omega, which is equal to rho 0 j omega s plus rho 0 j omega u and a certain delta. Okay. So what are we going to do to this? We are going to use the orthogonality. Okay. So we are going to multiply by another mode shape of the same basis and integrate over the volume of the cavity. Okay, that's what we are going to do. So let's do that. We have sigma n del square psi n x into a n of omega plus k square sigma n psi n of x a n of omega. Okay. Now we multiply this by a different mode shape psi p and dv. Similarly psi p dv and integrate over the volume. Integrate over the volume. We do the same on the other side. We have j omega rho 0 s x comma omega. We multiply by psi p x dv and integrate over the volume, and here we have plus j omega rho 0 u. We now put it as x bar omega, but choose the surface as delta y minus y bar, then psi p of x dv, okay, and integrate over the volume. So this way what happens is the velocity is as though a general velocity, but through the delta function I choose that particular surface, and so now this term becomes plus integral now over surface j omega rho 0 u. Now from x y bar has been chosen, then psi p P of y ds. Okay. Now we have to use a certain bit of information that is relevant to the mode shapes. So the mode shape, if you realize from your acoustics of interior spaces, okay, the mode shape satisfies the Helmholtz equation. This, you should know this. That means I am going to use the fact that del square of psi n is equal to minus k n square of psi n. Okay, this is very important because the derivatives suddenly vanish. You see, the left side is a derivative, the right side is a algebraic. Okay. Meanwhile, let me tell you that the mode shapes are as follows. The acoustic mode shape is for rigid walls n1 pi x1 by L1 cos n2 pi x2 by L2 cos n3 pi x3 by L3, where n1, n2, n3 are individual mode numbers in the x1, x2, x3 directions. Okay, this is for a hard walled enclosure, rectangular enclosure. Then the plate modes are simply supported modes, so they are sine m1 pi y1 by L1 and sine m2 pi y2 by L2. Now, just in case you have forgotten how this aspect works out, okay, I'll just give a sketchy proof or a sketchy derivation of this. So if we have del 2p by del x square plus del 2p by del y square plus del 2p by del z square plus a k square p equal to 0. That's your Helmholtz equation. And then we do this. P of x comma y comma z is given by x of x. We are doing separation of variables. Y of y, z of z, and we substitute it in here. Okay. So what we'll now get is x double dash y z plus y double dash zx plus z double dash xy plus k square x y z equal to 0. So if I divide the whole thing by x y z, so I get x double dash over x plus y double dash over y plus z double dash over z is now a constant. I put it on the other side. So this is exclusively a function of x, this is exclusively a function of y, and a function of z, which is equal to a constant. So each of these must be a constant. So I write it as minus kx square minus ky square minus kz square is equal to minus k square. So if I remove the minus, I get this. Okay. Now if I try to solve each one of these, okay, so that means x double dash over x is equal to minus kx square. If I try to solve that, that ends up as x double dash plus k x square x is 0. It's like a spring and a mass system. So this has you know, a cos kx x plus b sine kx x type of solutions. Okay, then we apply the boundary conditions. Applying the boundary conditions, we get values for kx which are infinite, not just 1. So it will acquire an index kind of kx. Let's say you know, p or whatever, acquires an index p equal to 1, 2, 3, 4 and so forth. Okay. So now what happens is I'll have kx p square plus ky q square plus kz r square is equal to, because these are indexed with pqr, this becomes k square pqr. Okay. So what that means now is that I have from here del square of x of x, y of y, z of z is equal to minus k square p q r x y z. So I'll stop here. We'll continue from the next class.